Okay, so yeah, thanks for joining seminar this weekend. And I'd like to discuss the one important like theorem. Yeah. Hi, Alan. Yeah, thanks for joining right now. So we are now uh, discussing, initiating the conversation about my note that I share. So what I'd like to do for this, like the March, is that so I use this as my primary reference for this, like the detail. I think this is also good, like the reference to keep for studying hyperbolic complex geometry. And I just look at the details of the chapter 4, section 6 to section 8 here. And Lempert theorem is there's a detail covered in these sections. Basically, I'm just summarize in my own way. So we can look at the details, not just today, but rest of this at least March to understand the details in our own like the taste and the preference. So the statement that we'd like to understand and the tools are is the Lempert theorem. So let me just fix the notation first. So D stands for the unit disk in C1. And rows of D stands for the Poincare distance that we already went over in the very first like the seminar. And there are two major invariant distances defined on arbitrarily complex manifold. So first, let me start from here. Characteristic distance. So the given complex manifold is the domain of the each like the holomorphic map. So that for each point we map onto into the unit disk and just measure the distance by the Poincare distance and take the supremum among all those like the choices. So such a like the distance is a characteristic distance, and the definition already requires the bounded holomorphic map. So there should be strong a structure issue. So for example, if M is just a C1, then by the Liouville theorem we know that there's no non-constant like the such a map. So it is just a zero. Same for Cn. So that characteristic distance, and if M is compact, then by just applying just the fact that the holomorphic map is harmonic, at least in the case of the Kähler, also there's no such a like the constant, like a non-constant like the map. So for compact complex manifold or like the Cn, so this is just essentially just a vanishing everywhere. So that the Kobayashi distance just change the location of the domain and the codomain, and then just change everything to be sort of the dual. So supremum is changed to just the infimum. The location, the position of the domain is now changed to the codomain. But the slight like the difference is that so now we check the partial sum, so that this is the finite like the many numbers of the chains to reach out to the chosen 2 points x and y. So in terms of the finite many holomorphic map from D to D2M, and just take the summation depending on the choices of this pair. So this is the concept of the Kobayashi distance. And if you ignore this like the summation part, so one can still define the infimum of the rows of the in the same manner. That is called by the so-called the Lempert function. Lempert function, in general, this is not becomes the pseudo distance for the Lempert function. So finite summation is required to make it to the triangular inequality to be satisfied, and basically that's the reason. So it's not difficult to show in general for arbitrarily complex manifold. It's just a consequence of the classical Schwarz lemma that characteristic distance is always less than or equal to the Kobayashi distance for arbitrarily complex manifold. That's just a very easy fact to check. And the Lempert theorem says that if the complex manifold is biholomorphic to any complex domain in Cn, then those two pseudo distances must be coincide each other. And the equality also holds for the metric version, local version as well. But I think the distance version gives us more intuition. So I want to just go over the just a comparison of the distances, basically. And this is the theorem we'd like to understand the details. And I also want to mention that so once the Lempert theorem was established, so people in the community of several complex variable ask, then this condition is indeed necessary condition required. And it turns out to be no, that so there are the complex manifold which are never biholomorphic to any complex domain in Cn, but still they could be the same. So two primary examples at this point is a symmetry by disk and the tetra block. Those two examples of the C linear convex domains are important in a sense that they serve as a counter examples of the Lempert theorem in some sense. So that the equality of the distances are not implying the convexity, basically. So that makes the more interesting to understand the or many classes of the bounded domain in CM basically. So this is the like the theorem in several complex variable. So are there any questions regarding just the statement or any comments? So rest of the note are about the detail, how to prove this guy. So let me just directly jump into the conclusion. So my purpose is not just look at the just a line by line together. I think I don't have to. So what I want to do is I just want to introduce and explain the basic structure, how to read this note. And we can just, if you have a time during the week, then we can just go over the note in our own way. And we can just try to make the discussion, not only understanding the line by line, but also try to imagine if you can push some interesting like a direction in terms of the research. Then we can just initiate some like the very interesting like a conversation on it. So the proof is the following. So the way to prove is that, so there is a concept. So the equality of the two distances is the consequence from this theorem. And the numbers of this theorem is from the reference. I just match the number of the theorem from the reference so that if you want to compare the primary, like the original reference, then you can just look at that. So there is a concept of the complex geodesic first. And then there is then this theorem says that then we can find a holomorphic map P tilde from the given complex. You can just also access just a complex like the manifold, but basically we just look at the convex domain in CN for the as an application. But anyhow, this is a complex manifold. So given a complex geodesic, then X to D, we have a holomorphic map such that, so because this complex geodesic is a holomorphic map from D to X, we can compose them, then it becomes the identity on the unit disk. And if we compose in this way, then we have the so-called holomorphic retract. So let's just assume this is the case. And let's just go over what's the definition of complex geodesic. So the complex geodesic is over here. So first, so we start from the complex space, but complex space just means the complex manifold allowing finitely many just a singularity, just a points, but you can just also use complex manifold basically. So it might be able to extend to the case of the complex just stacks, but we don't really care. So it's just complex manifold. So we pair, just fix the pair from the complex like the space capital X, then we say holomorphic map from D to X is the extremer disk with respect to this pair if we are able to find also the pair from the unit disk such that each of the points maps to the given pair, and the Poincare distance of this pair coincide with the Kobayashi distance. So if you compare with the definition of the Kobayashi distance, it first requires a finitely many like the summation part from the chains depending on the pair. So this summation becomes just n equals just 1 first, and we are indeed able to find the holomorphic map realizing this infimum. In such a case, we say such a like the map is the extremer disk. So I just also use the same terminology from the reference. And also there's a extremer disk for the local version as well. If we just replace the pair to just the tangent vector, that's it. It's the same concept. Then we have also the concept of complex geodesic for the single holomorphic map. Single holomorphic map, that this single holomorphic map from D to X indeed becomes an extremer with respect to any pair. That's the definition of the complex geodesic. Is it okay with you? So the complex geodesic indeed realize the Kobayashi distance by this single map for arbitrary pair. That's the definition. So now let me just go back to the second. So now we know what the complex geodesic really means, so that we have a complex, so basically convex domain in Cn here. And because we already have assumed that such a map exists, then this theorem says that we have some nice like the holomorphic map that changes the location of the domain and the codomain, satisfying certain property. So let's just assume for a moment that if we are able to find such a like a holomorphic map, then what happens? So let's just simply just assume, and rest of the detail is in order to just find such a holomorphic map. So why we obtain the equality? As I already said, Cartesian distance is always less than or equal to the Kobayashi distance. So that in order to establish the equality, we just need to flip the inequality. So that what we want to do is, so we already said that according to the assumption, so for arbitrary pair, we already know that such a like a complex geodesic exists. That's the assumption already. Then we start from the Kobayashi distance. Kobayashi distance. Then by the definition of the Kobayashi distance, this is defined as an infimum of the summation of the Poincare distance by its definition. So this inequality is just followed from the just the definition of Kobayashi distance. Of course, here actually we use the convexity that this is defined as a finite summation for taking the infimum. But in the case of the convex domain, the finite summation is actually just a removed because of the convexity assumption. So this is just a consequence from the definition of the Kobayashi distance. Then what we also have is that this A and B according to this condition, so that we can simply just replace the identity map by this guy. It's just a trigger because we already know this one already hold. This is fine. Then what we also know is that characteristic distance is defined as a supremum from X to D. And we also have another holomorphic map P tilde. Then by the definition of the characteristic distance, we can simply just remove this P tilde. And this is also one of the possible choices. And this is a supremum. So we get this. So once we write in this way, this is just a X and Y. So we establish the comparison. That's all. So what we, in order to establish this guy, then we should get the holomorphic map from the given convex domain to the unit disk. So we have a bounded holomorphic map first. And then this condition, as you can see, this condition is required. And this condition is sort of the necessary condition to get the well-defined map if we just flip the location of the composition. So now then let's see why this such a like a holomorphic map, such an existence must be guaranteed in the case of the convex domain. So the detail can be just behind hidden from the proof. So let's just also directly jump into the like the proof of the theorem and why the some function analysis argument might be required. So in order to find such a map. So let's just look at the theorem. So the details indeed coming from the single variable calculus. So it's the following. So let me first give you the definition of the dual map. I'm not talking about the just or like the necessary like the details. So let's just really look at what this means. So we assume we already have a complex geodesic, and F tilde is defined in terms of this complex geodesic. So the definition should be somewhere here. Yeah, here's a definition. So we start from the complex geodesic. So I also fixed the notation, what each of this like the method notation really means. So the notation I just mentioned here. So also I use the same notation from the primary like the reference. So each of the notation just this capital H means the just not the overlap space, but just a holomorphic map. So it's just Kobayashi use that notation. So for example, we are familiar with such a like notation A of D. So A of D just means a holomorphic map on the like the chosen like the bounded domain in Cn. D just means the bounded domain in Cn here, and it each holomorphic extends to the basically just the boundary up to continuity. So that's the notation of the AD. And H of 1 just means that we have a holomorphic map. It is just an L1. H sub infinity just means the L infinite function, which are holomorphic. So definition is pretty much simple. And if we choose the product notation here, the power just means we have a map from D to Cn. Sorry, it seems in my notation this just stands for the unit disk. It's just a C1. Sorry, so just a D means a unit disk. So this notation just means D to Cn, and each of the components satisfy the condition. So that if we just put the power n, just means that each component satisfies the condition. So that this naturally brings our intuition to the so-called hard disk space, if you are familiar with the hard disk space already. So let's just skip the detail for a moment. So let's just go back to the definition again. Where was the definition of the dual map? Yeah, here. So we have the complex geodesic from D to just a bounded domain. Then F tilde is defined as some weird like the function. This H satisfies certain condition. Let's kind of forget about it. So this is important detail, but this gamma sub like the not gamma sub 0 just means the following. So gamma not is basically this kind of the guy. So, but let me just so uh, this guy. For example, this guy notation. So this is a notation of the divisor so that it has a zero at the origin with the power of 2. That's the meaning. So this notation just means the t squared. So if this number is just 1, then this just becomes t. So that you can just assume this guy, gamma naught just means it's just nothing but t. For example, so the power of the order of at the origin is just a 0. That's the meaning. So there's some holomorphic map here. So this is just follows from some details from the functional analysis that we should look at. So it's kind of the t times some holomorphic map. That's just the definition of the dual map for a moment. So now let's just really look at this condition. So we start from the complex geodesic here, and then we have a dual map. Then what we want to do is we create the complex hypersurface satisfying these conditions. So we collect, so for each t, this t is the point from the unit disk. So we fix the arbitrary point from the unit disk, and then we just set up the one equation in Cn. So this is the inner product, but not the Hermitian inner product. So we don't put the complex conjugate on the second like the entry here. So also this is also written in my note. So this inner product just means the non-Hermitian inner product without the complex conjugate here. But still, this just gives a one linear equation. So this is a complex hypersurface. Complex hypersurface. So this F is the complex geodesic, and this F tilde is the dual map defined by certain like the condition, and we just gather all possible Z satisfying this equation. Then, so if we just assume that the dual map satisfies this condition, so F tilde is actually never 0. So this follows from the construction of this dual map. Let's just formally just accept this as a fact. That we need to eventually really check. So this condition is guaranteed, so that this now becomes a non-trivial complex hypersurface because this is never 0. Never 0. So that this is a codimension 1 condition. If this is 0, then this is a redundant like condition. So this is a hypersurface. Then what we'd like to show is that by using the definition of the dual map, so let's assume we can show this claim. So what we'd like to show is that for each point, Z, for each point, we are able to find unique point from the unit disk, satisfying this hypersurface condition. So by using just the property of the dual map, so let's just assume we are able to show this. Then let's see what happens. This condition just really means, this condition means that we actually have a what? Map. We have a map from Z to T, satisfying some inequality, some equality. So this brings our intuition to the implicit function theorem and also the inverse function theorem, basically, at least locally. So then for the complex structure, so if we already have either the implicit function theorem or the inverse function theorem, the holomorphicity that just follows. So the usual multivariable calculus version is for the in the case of the smooth category, but holomorphic category is just extended automatically. So that the inverse function theorem also works for the holomorphic functions as well. So because of that, so for each Z, we are able to find the unique point satisfying this condition so that we can apply either the inverse function theorem or implicit function theorem. So that we have a map from Z to T. Let's call it by P tilde. Then as a consequence of this theorem, we know P tilde must be holomorphic because this is a complex hypersurface. Then what we can immediately check is that because if we just replace this Z by f of t, then this is clearly guaranteed because the second slot is just as being 0. So if you just think about what's the implication of this condition, this just means that P tilde ft should be equal to t because of the uniqueness. So this shows this part with this part and the proof is over. So now the key is what? The key is how can you find the dual map satisfying these conditions? So here are just two pieces. Number one, for each z, we should be able to find t. Number two, such like the t must be unique. Then we know how to handle because we have an equation. Then first, the uniqueness is coming from, actually it's also related to the existence behind. So it's coming from the winding number. So if you look at this condition here, as I already said, this f tilde is defined as something like something such as T times H of T. This H is some holomorphic map. So let's just use that condition. So let's just use this condition to define the holomorphic map for each like the Z. So we fix now Z. So Z is now the fixed like the variable. And just let's just assume this is a holomorphic map with respect to T. So this is the unit disk, the holomorphic map defined on the unit disk, which is a complex value for sure. Then as I said, so this contains T as a component. So we just can take this T out. T out, still this H is holomorphic. Then what we'd like to show is that this is indeed degree 1, power 1 at the origin. So in order to show it, we need to say this is always non-zero for any choices of T. So by using the property of the dual map here, so that we need to use the property of this H to show this is never zero for any choices of T, then we can say that then this has a power of 1 at the origin. So this gives the proof of the uniqueness and the existence as well, so that we can use the winding number argument from the Cauchy integral formula, and by just combining the fact from the previous the details, then we are able to show this is never zero. So therefore, the winding number is equal to 1. Then we are able to establish this claim. That's the idea. So that we have a basically hypersurface condition, and from this dual map, we just want to take this T out, and except this T, others are never equal to 0. Then by using that condition, then we are able to show this claim. So then what's the necessary condition? Then we need to show, we should construct such a the desired H here, such a desired H here that satisfy the condition here. Then we are done. And in order to find such a the H, this detail is not easy. So this H is coming from, now let's see where this H is coming from. This H is this guy with this weird messy notation. This H is related to the complex geodesic. So because we assume there's a complex geodesic, so that we are able to find some massive function. This is a desired H that we already use. So that in order to get that H, then we need to get this or equivalent statement. And then how can we obtain this equivalent statement? This is coming from the Han-Banach theorem. So the origin is coming from the Han-Banach theorem in functional analysis. This should be here. So I skipped the proof of this the theorem, but if you want to just look at the reference, then it's just a consequence from the Han-Banach theorem. So what we use is this so-called principle of the duality that establishes these 3 statements that gives the existence such a H, then that gives the proof of the Lempert theorem. So the punchline, and I think this proof is very worthwhile to understand in detail, because the Han-Banach theorem, this is an application of the Han-Banach theorem, so that we just make everything to be fit to this the setting, and then we are able to find the H, and the detail is just a Cauchy integral theorem and Cauchy integral formula basically. Our the strategy therefore is, in order to apply the Han-Banach theorem, we just look at the setting of this guy and apply this the theorem for the just making the setting. So there should be a certain I hope there's a certain freedom that we can adjust the setting slightly to get some more interesting implications. So that's a basic idea. So let me just summarize just again. So the equality is consequence from this P tilde. This P tilde is coming from the dual map. This dual map is coming from H with T. This H is coming from the principle of the duality. Principle of duality is coming from the Han-Banach theorem. So that's the big story. And the Lempert's original argument was also using the functional analysis the technique. It also relies on the Han-Banach theorem, but it's written in French first of all. It doesn't mean that French is hard to just read, but it's very hard, in my personal opinion, to understand just line by line. So I think this argument is more like the structure to understand what was really going on. So that we will just look at the now setting line by line. So any questions? So that's the basic the structure. Yeah, okay. All right. So then what is our goal? So after we understand it like the each like the statement and the setting, then our goal is just nothing but applying where it should be just to apply that principle with a certain setting of the convex domain. So and my base like a perspective is not just understand the line by line of this argument. There should be certain like the freedom so that you should like think of where's the like the location of the logic that we use the for example the convexity and for example so all those like the kind of things should be like thoughtfully like considered. So now let's look at what we can do. So now we have a extremal problem. So we start from the complex Banach space. And even this very first, like the line of the definition makes me actually wondering. The definition is intuitively very clear. So we have a Minkowski functional. Minkowski functional basically it satisfies these conditions. So it has a sub-additivity, and we have a sort of the linearity, but it's not the case because this linearity only works for R non-negative real. Even this is a complex Banach space. So this is not in that reason, linearity. Is that okay with you? So we only guarantee such a like the condition for the non-negative real. And still we are able to compare with the given norm because this is a Banach space. So that, as I said, this is not norm in a sense that if you just put negative f, this is actually not equal to p of f. So this is not the norm, but still we have a comparable condition. So you can kind of assume that this is a non-symmetric distance, so that intuitively this behave as a distance, but rigorously not, but it's sort of similar. So in order to establish such a, like the Minkowski function on the complex like the manifold, this is already non-trivial. So the setting we already use the domain in Cn. In such a case, we are naturally we can actually construct such a like the Minkowski function in this argument. But even for the complex manifold, I do not know how to actually handle this guy from this node. But anyhow, let's just move on. So what we then want to do is we choose just a linear subspace called by M, linear subspace. Then after taking the closure, we just look at the complement. So let's just this is a proper subspace, so that we choose F naught from the complement of M, like the M closure. So let's just choose that. Then what we want to just find, so this is this ultimate desire that we'd like to find. We'd like to find the infimum of all those choices of the F inside of this M that makes the distance from 0 to here to be minimized. Indeed, intuitively speaking, so F naught is chosen from the complement of M bar, so that and we just add as F naught plus F, and we just look at the smallest possible like the distance, sort of. So hopefully this is intuitively okay. So the linear extremal problem is to find F that realize such an infimum. That's the problem. So because this is now the infimum, so it is very clear that we are in general not able to find such an infimum. So the strategy is that in order to find such a like the M by just finding some of the elements here, because it's not in general guarantee, so we look at the dual space. So the duality argument plays a role. So the duality, in order to use the duality, so we have a complex Banach space here. So take the dual, another complex Banach space here. Then what we want to do is we already assume we have a complex Minkowski function defined on this L. We just assume we already have it. Then we define the dual Minkowski function P star coming from L star to R. So it's defined in this way. So it's just a dual one, just a dual line, just the argument. So from this condition, so that we can easily see that from this map, so we can also take the dual of this M. So this is an annihilator of this M. So that just means that for any element from this M, so if we just look at the linear functional, we just make it to be 0 and just collect all of such like a U. And this just M to the just a 0. So we make another like the infimum of all those choices of P star U, that this U is coming from the annihilator of this M. and satisfying this condition equal to just a 1. And take the infimum of this M star. So the dual experiment problem is to find U satisfying this condition, and it realized this infimum. This is a dual problem. So the ultimate desire is to solve the linear experiment problem, but in general, this is hard to solve. So we just look at the dual problem. So here's the principle of the duality. So what we want to do is, so we start from the complex Banach space, and then we have a arbitrary Minkowski function, and choose the proper subspace, and then choose F naught from the complement of this M bar. Then first, each of the M and M star are defined as the infimum. So those are at least were defined as in the extended like the real number system for sure. And those are just the reals. So that M times M star is equal to 1. This is already guaranteed. Number 2, we are always able to solve the dual experiment problem. This statement says that we have no guarantees to solve the linear experiment problem, but always we are able to solve this problem. So we are always able to find U solving this one, so that we have certain benefit. This completely solve the problem yet, but at least we have a sort of the progress to solve the original problem. So we'd like to take the benefit. Then with that perspective, if you look at the last like the sentence, so this is now the assumption. So what if we are able to find the F coming from here? So this should be chosen from this guy, this space. And we have the U from the annihilator of this M, making these two equals to 1. Make sure that we already make this is equal to 1. And we don't know yet that we are able to find the small f satisfying this condition yet. But suppose we already find this guy. Then, in fact, this solves the linear experiment problem. That's the last sentence. So this condition can be checked in a sense that Minkowski functional is already given. P star is also defined in terms of Minkowski functional. And we already have the natural candidate of U. So all we need to find is what if we already have the natural candidate of this U here. So that what if we find the F that's satisfying this condition? Then we know, at least in this case, we solve the linear experiment problem. So that in that sense, we take the benefit from U that by using the condition of U, we are actually solve the original problem. So that's the strategy of the principle of duality. And this like the statements are the consequence of the Banach theorem that I skip in this note, how to prove this like the statement. So what I'd like to do basically, but if you want to look at the details of the Banach theorem, I'm very happy to discuss about it as well, but I just want to apply this theorem for this note. So is that okay with you? So for today, let me just fix the setting. So let's just accept this as just a fact that we just want to apply. Then in order to apply this theorem, then we need to just establish each of the setting in the setting of the bounded convex domain. So you can just assume if this just convex domain is just an entire just a Cn, this condition is just trivial. It's just a 0. So we just assume that this is bounded convex domain for just a simplicity, so that these two distances are non-trivial in that case. In that setting, we just need to establish all of the the settings of the what is L, what is the Minkowski function, what is this M, and so on. Those are required. So let's try to now make it to be happen. So first, but before moving on, so any comments or questions? So this is a primary like the theorem bit we'd like to apply. Any comments or are those all okay? So it seems kind of clear. Okay. So for today's conversation, I just want to fix just the setting. So what you can see from here is, as you can see, here's L, here's M, here's small m, here's small m tilde. So that now we just need to establish what each of the notation here really means. Is that okay with you? So this is the setting that we'd like to apply the principle of duality, so that I just need to explain what each of the notation here really means. So now let's look at this guy first. So this guy is coming from the Cauchy integral theorem. I should say Cauchy integral formula. So let's just look at the notation. So the first what we have, so let me just look at again. So this L is this guy. So let's look at this node first. So first, this L1, so this is just a general fact. So this distance for the unit disk is C1. So if we choose the L1 function on the just the S1, basically, then we can use this H to take the boundary integral, so that we can just map to the just the dual of the continuous functions on the bound on the just sphere on this S1. And one can show that this is actually isometric emergent because each of them are Banach spaces, so that there's a concept of the norm, so that norm is also preserved for each like the Banach spaces. Is that okay with you? So that we first have the isometric emergent in this way in general. And then by using this fact, what we can do is this A of D just means a holomorphic map on the disk that extends to the boundary in the continuous way. So then we know that in fact this should be embedded into the C of AD because we have the Cauchy integral formula, so that if we already have a holomorphic map, then we know that it is determined completely from the boundary data. This is just a direct consequence from the Cauchy integral. That's a formula. So that we also can identify this A of D inside as a subset inside of here. This is our guarantee. And this complex Banach space is chosen to be L. Now we have a choice of the L here. Then we also need to choose, what's the next step? We need to choose this guy. Is that okay with you? And what is this notation, by the way? So this means that, so each component just satisfies this condition. That's the meaning. And because we have a bounded convex domain in Cn, each component function just satisfies this condition. Then we can apply the Cauchy integral theorem component-wise. So that's now, I assume it's clear. So now we need to look at this guy. What is this guy? So this condition is coming from here. So let's look at what this notation really meant. So it just means this guy. So first, you should assume this is not the summation of the complex numbers in this definition, but as a divisor. What this notation really means is that because if you choose arbitrarily like the points from the unit disk, this is in general not guaranteed. So this just notation just means that at the point A, it gives the 1, 0. At point B, it gives another 0. So this is the summation as a free abelian group, as a divisors. So that what we want to do is, so for this divisor of the pair A and B, we'd like to make the corresponding holomorphic map so that if you just plug in either A or B, it just becomes 0. And we just use the Möbius transform to create the bounded holomorphic map, because we know each of them just maps to the unit disk. So even if we take a product, it still sit inside of the just D. So that we just create the bounded holomorphic map whose zeros are A and B. We just create such a like the map and just call it by the gamma. And when we use this notation just means that for each holomorphic map from this to the convex domain, then we just multiply by this guy. So why we care? So that in that sense, if we just plug in either A and B from the unit disk, this is guaranteed to be 0. So why we want to do that? So the reason is that eventually what we'd like to make is we want to control the complex geodesic. And the concept of complex geodesic is for the arbitrary pair to be extremer. So what we want to do is, intuitively speaking, so this X is the bounded convex domain Cn. So we eventually will use the complex geodesic. So but it's just coming from the extremer disk. So we fix the pair. So that in such a like a pair, we are always able to find the pair from the unit disk. And we just want to control this pair. So that's why we just assume what's the just put this guy to control the pair from the extremer disk and even therefore for the complex geodesic. So that condition is over here. So then what is the notation of this guy? So we have this one. I just simply just write as just a triangle. It's just the omitting the notation of this guy. So we fix the A comma B the pair, and we just get this guy. Then we have this definition over here. So this is also another so this also belongs to L. from our like a previous argument. Is that okay with you? Because if you have a holomorphic map extend to the boundary continuously, then by using the quotient integral like the formula, we know that each element here belongs to here. So now we establish the complex Banach space with the proper subspace. Proper subspace is also very clear because these are not in general holomorphic functions, whereas this is holomorphic, so that it must be proper. This is also now a guarantee. And also, what we should fix is m and m tilde. In order to do that, we need to find the Minkowski function. So now we have this guy and also this guy. So now we should get this. So where is Minkowski function? So it is defined in this way. So now we first use the convexity. So now let's assume we have a bounded convex domain and we already assume it contains the origin. This condition is also required to use to define the Minkowski function. Then for the convex domain, this is a good exercise in my opinion. This is a not that difficult exercise. And if any of you want to look at the details, I'm very also happy to look at it together. It's not difficult. So then we can define first the Minkowski function. This is defined from the Cn to R. And so if we have a point Z from Cn, then just look at the infimum of the R to the -1. That makes Rz belongs to X because X is already chosen. And if you just define such a map in this way, then it's not difficult to show by using this definition, this X should be realized as a P is strictly less than 1. And here one need to use the convexity in order to establish this equality. This is, I think, very good like the exercise from the function analysis, the elementary like the exercise. And one can also show that for the Minkowski function here, not the function yet, so by using this guy, then one can also establish the necessary condition of the Minkowski function first. Those two conditions of these two. Even we don't have this yet. So this is a previous stage of the constructing such like the function. Is that okay with you? So how to logically this works so that we have a bounded convex domain. Then for the Minkowski function, by using the convexity, one can establish this guy. And also by using just a definition, one can also establish all necessary conditions by using this infimum. And from this construction, you can see why we need to require the non-negativity because this is defined in terms of the infimum. So for the complex like the value, we do not have control. So there is already the sort of the obstruction if you want just to take the variation of this like the construction. Then we also have the dual Minkowski function, P star. This P star is also follows from the just a fact from the functional analysis. Then we just get this. We just get this. So and from this condition, now you see how this denominator condition plays a role. So that this is a scaling condition, so that we can simply just assume that this piece of X, I mean this guy, is just equal to 1. Then because of this identification, we can just take this Z is sit inside of the boundary of the bounded convex domain. So now we use both convexity and the boundedness. Again, for the non-bounded like the convex domain, so the consequence of the Lempert theorem is just automatic, so we don't care. So for the bounded convex domain, we already use the two conditions to define this guy interestingly. So we already used the boundary condition. All right. But at least it does not require the smoothness of the boundary. But there should be the boundary. That's what I'm saying. Then now this is an interpretation, but I just want to directly jump into the Minkowski function. So then what's the Minkowski function? Then we already have L. So even I just use this guy for the L, but for our like the setting of the theorems, we can just replace that guy depending on the setting. Then anyhow, either we take this to be the L, or as I said, this to be the L, doesn't matter. Then what we can do is we define the Minkowski functioner for each like the functions, just take just the f of t for each like the point of the unit disk and put it into the Minkowski function and take the supremum. So that now you see we use all necessary data of the bounded convex domain. Then for this definition, because we take the supremum, because Minkowski function already satisfies this condition, so that automatically it satisfies the Minkowski function necessary like the conditions. So that we have now the definition of this P. once we have the definition of Minkowski functional, then we already have the definition of dual Minkowski functional as well, because we already have this capital P here. Then now we have all necessary settings. Let me just double check. So that now we have a L, we have a M, then we have a P, and we have a P star. So that these two should be also established. Then we have a setting, then we can apply. Of course, it depends on the each of the settings. So there's a certain the variation of this the details of the argument. But this is today I just want to go over. Then one can just apply this theorem, and there are certain the remark and the properties for each of the construction. I mean the properties and some the subtle the details to think of. But yeah, basically that's the way to do it. So Lempert, the original argument is not based on the principle of the duality, but the basic line is still the application of the Han-Banach theorem, basically. But this the argument is some clever way to apply the Han-Banach theorem. And this just gives the very a precise way to just make the setting in terms of the L and M and P. And by using this guy, then one can solve this a problem. That's the basic the way. And such the linear experiment problem is the desired the solution of the H of the dual map that gives the proof of the Lempert theorem. And I think this the proof is very worthwhile to look at. Yeah, so this is today I just want to go over. So if you are busy, so it's okay. You do not need to read my note, but rest of this last 2 weeks of this March, I want to understand this note line by line. I think this the detail could be very worthwhile to understand for the understanding several complex variable. Yeah. So any other questions or comments for today?
Just for my own sake, let me try to put together what we've seen today. So the proof of Lempert's theorem basically boils down to uh, an application of extremal problem
Yeah.
in a specific setting.
Yeah.
And the application of a solution to the extremal problem comes from Han-Banach theorem. That's unnecessary. So once we state this principle of duality, whatever the theorem that is here, the next setting is to define the exact L, P, M, and other things in the context of the our domain, the assumptions of our domains, and ensure they work fine. So and then we just apply. So this looks beautiful.
Yeah, this is very clear. So as I said, so such the solution of the linear experiment problem gives this P tilde. And this P tilde is written, I mean, this H is a solution of linear experiment problem. So this is the construction. Yeah. And just it's all consequence of the quotient integral formula, by the way. So I also like that. But it also gives the obstruction to extend to the complex manifold case, because the complex manifold case, there's no quotient integral formula in general. So this argument actually fails. So, but I actually hope there's a way to actually go around. And also another necessary question is, for example, so the concept of the complex geodesic itself does not require the convexity as well. So, for example, Kobayashi distance and the characteristic distance are the same for the symmetry by disk. So some of the references investigated our complex geodesics are symmetry by disk, because we know they are the same. And this equality is coming from the complex geodesics still, even that's not and never by holomorphic convex domain. So there should be also the possible the extension, in my opinion, but because of my lack of the imagination, I do not know how to push further. But hopefully there's a less the next interest the application. Yeah.
Can you just say it again? Of what do you expect to generalize, or what do you expect to push further? What is the current thing, and where do you?
So it could be completely wrong. It's just my very vague and naive the opinion. But at least Lempert's theorem says that if we have a convex domain, then they are the same. Then we already know that this is not the necessary condition. And at least symmetry by this serve as a counterexample of this theorem for the converse direction. But at least for the symmetry by this, we know they're already coincide. Then so when they are coincide, so the proof already actually implies, even though this is just a sort of the heuristic, so because we already lose the necessary setting for the symmetry by this, for example, how to prove this equality? So already it's hidden that we should find complex geodesic in the case of the symmetry bias, and actually this is already case for the symmetry bias. Some of the paper already investigated all complex geodesics of the symmetry bias. Then once one find the complex geodesic, then by just applying just the context of this, like the argument, one are able to show this guy. So the complex geodesics, as you can see, is sort of required, but already this argument does not work for the symmetry bias, rigorously speaking. So that it means that there should be the way to extend this theorem, in my very naive opinion, more like a larger classes. But even from the beginning, it fails in a sense that in order to find this Minkowski functional, we should start from the Minkowski function. This is a natural choice from the functional analysis, but this like the setting is already failed for the symmetry bias. But it does not mean that this entire argument should be failed. So then what is the way to go around? That's my very like the naive. So yeah, I want to remove this condition, but I don't know why, how. Yeah, so that's why one can look at the details. So about, yeah, I'm very happy to discuss in terms of the imagining this like the subtleties. But yeah, that's one thing. Yeah, any other comments or Verity, if you have any comments, let me know.
Yeah, I have no comments.
Okay, sounds good. So for at least two next weeks, we will look at this note over and over together. And if you have any like questions on the details, yeah, I'm very happy to clarify all of the details. Yeah, let's stop to here.